All right, hi everybody. This is lecture 2. So in the first lecture, we talked about where does elasticity come from at the atomic scale. And we got a little bit up to sort of slip planes and thinking about the geometry of slip planes and how we could come up with a geometric expression for a shear stress. That if we apply a shear stress of that magnitude, then it would cause the plane to slip. And that would be different for different materials. It's based on bond structure, right? What type of bonding there is. And it's based on the crystalline structure, right? Face-centered cubic, body-centered cubic, and things like that. The understanding those things can sort of give us a guide as we move forward and think about how do materials respond under some of those general categories I introduced last time, right? Forces that may be steady or transient or cyclic, temperatures that may be steady or changing, and things like that. So I was taking a look at the overall trajectory of the course. And we're not going to talk much more about dislocations, actually, because there's no direct connection to, let's say we're doing some sort of fatigue analysis or something later on, where we come back and we say, oh, remember the screw dislocation motion, right? So we're not going to be able to connect that explicitly. And so we're not going to spend much more time talking about dislocations and slip. And I think I tried to post this on the class website as well. We're going to move more into like defining stress states and solving problems so that we can start to characterize the stress in a component and then talk about in what ways it might fail related to the stresses that we calculate. So I have 2 more slides on talking about dislocations and materials. So last time we finished up with this equation where we had a critically resolved shear stress, or I'm going to just write it how the book writes it. They say critical resolved shearing stress. I'm just going to explore one thing here. All right. I was going to see if I could make the pen bigger, but I don't know how to make the pen bigger. So we're just going to write bigger. Okay. And that was like a tau, right? Come on. Tau. Oh my gosh, every time I touch it, what's happening? Okay. Tau, there we go. So tau r was equal to, right, the force at the end of a bar divided by the area of that bar times cosine of lambda times cosine of psi, right? And I can just drop the bar real quick again, right? So it's just this cylindrical bar with a force applied at the top and bottom and some area A at the top, over which this tensile load is applied. And then we identified some slip plane in the middle like this. All right, so you should see that in your notes, right? And then if there's a normal to that slip plane, then that's defined by an angle psi off of the direction of the force. And then within that plane, right, it can slip in any direction. And so the slip direction was also defined off of the vertical. Like let's say it goes like this. And so the slip plane defined off the vertical was lambda. Okay. And so these kind of things can be determined for a particular material. Are all the screens flashing or is it just one? Okay. I keep looking over and thinking it's not there. Okay. So I wanted to mention a little bit about some other effects that will come into play a little bit later on. So one is strain hardening, and then one is temperature. Okay? So we're going to leave behind thinking analytically a little bit about strain hardening and about dislocations and slip. And we're going to talk about these two other effects briefly. The first one is strain hardening. So I'll go to the next slide. And so we know of strain hardening as a material is plastically deformed and it becomes harder in some way, right? So that can mean the yield stress is increased. It can also mean that the modulus of elasticity changes, but the majority of the strain hardening is going to be in the yield behavior. Okay? And so if we make a plot that's related to that critically resolved shear stress, that's going to be on the y-axis. So I'm just going to write tau r, right? So that's kind of, just think about the ideal bar that we had. That's the same, it's the same type of, it's the same magnitude. And then on the y-axis, we're going to have the resolved shear strain, right? And so shear strain, I'm going to call this like lowercase gamma, and I'm going to call it R because it's resolved in the slip plane. And we can then draw kind of a characteristic curve for different materials. Okay? So let's first talk about something that doesn't have a lot of strain hardening. So that would be like a curve on the bottom like that, right? And one example of that is magnesium. And it has linear strain hardening, and it's also not very extreme, so it's a low magnitude. Okay? So the more you have shear strain, right, along the slip planes, the higher the resolved shear stress you need in order to keep having that slip. All right? So the interface gets harder to slip the more you slip, right? So that's kind of a layman's terms of strain hardening. And we can have another one which has kind of a fun behavior, which is copper. So if you've ever played with copper or done an experiment with copper, you know that it's very ductile, and so that also comes into play in its strain hardening behavior. So I'm going to draw kind of a curve with a couple of different inflection points like that. And so you can kind of divide it up into different regions, right? Like stage 1, stage 2, stage 3, and this would be for copper. So I'll write copper there. Where you have kind of a stage at the beginning that has an increasing slope, but it's very easy to have the slip, right? And then there's a linear hardening regime, which would be that second stage. And then there's a kind of a plateau or a flattening when you get out to the higher stage, right? And this mimics a lot of these types of phenomena that we would see in engineering materials. Like if you think about creep and you think about things like that, they'll often have a few, for these extreme materials that have these properties, they'll have a few phases, right? And so this is the same thing here for strain hardening. And then at the top, there's also, you can have sort of a decreasing one, right? And so if we put Fe, we put iron here at the top. Sometimes this is called parabolic strain hardening, and it has a decreasing rate the more that you go up. Okay. I didn't put the numbers on these axes, but in our textbook they do provide the numbers so that you can see. So I'm going to anchor the x-axis by a value of 0.6, and so that is very, it's very high strain, right? And so this thing has slipped like very, a lot, right? Usually we talk about the stress strain curves for a tensile test, which we'll go over in detail, right? We define the yield strength on that as something like 0.2% yield, right? So this is 60%, so it's exceedingly high. So down here where we talk about like sort of first yield is going to be way down here, right? And then the resolved shear stress in PSI, right, is going to be anchored at the top of this plot, something like 12,000. So I'm just going to write 12K. So we can get very significant strain hardening, especially in iron-heavy alloys like steel, right? So we sort of know that already, having studied some of these materials. And then the other effect I wanted to mention briefly is temperature and what's called material recovery, okay? So I'm going to go to another slide here. So when you heat up any kind of ductile metal or metallic alloy, something happens, and which is the things internal to that alloy or metal, the grains start to kind of shift around with respect to each other. There may be local melting, but there's at least movement. So recovery is, the technical definition is that the grains reduce their stored energy by the removal or rearrangement of defects. So by removal or rearrangement of defects. Sorry, handwriting is bad. And so we talked about these slip planes, right? So if a metallic alloy undergoes some sort of stresses that would lead to those local microscale slip planes, and then it's heated up, right? It's tempered at some temperature that has been studied and shown to induce recovery. Then some of those defects that we introduced in these slip planes are basically going to move out of the way, like move to the grain boundary, and the grains will shift slightly to reduce their stored energy. And so when that happens, I'm just going to draw a plot here of the shear stress and shear strain, kind of like what we had before. And I'm going to draw the strain hardening at different temperatures. So now we can see how that manifests. Okay. So we're going to talk, this is a plot for single crystal aluminum. Okay. And then we'll start at something, if this is on a Celsius scale, we'll start at kind of room temperature, right? And so it will have strain hardening up to some value, and this is parabolic strain hardening. And that value is going to be, I don't know why they changed the units in the book. This is wild. This is now in kilograms per millimeter squared. Sorry, I didn't have time to do a conversion. And that goes up to about 3.5. Okay, and I'm going to write like 18C. It's not exactly room temperature, but it's closest as we can get on this chart. So as we start to raise the temperature, so now we have this material at a steady state temperature, and we start trying to make it slip. We don't get quite the amount of strain hardening that we got before. So this would be like 100C here. So it's about half the amount. Sorry, let me say that's about 200C. It's about half the amount. And then once we go up to temperatures close to the softening temperature, like 500, 600C, we're way down here, we get almost no strain hardening, right? And that's because as soon as we slip and create those slip planes, the material relaxes back to reduce its stored energy because it's so hot, right? It has that mobility at the higher temperature. And then conversely, if we were to put this bar at a steady state temperature that's very low and then try to slip it, it would undergo exceedingly high strain hardening. So let's say this is like minus 185C. Okay. Then it's up at like 6.5. So the extent of strain hardening is related to not only the type of material and its crystal structure, but also the temperature it's at and its ability to recover. Okay? And so these are concepts that are introduced in the book in chapter 3 because they're related explicitly to these atomic origins of plasticity. But we're not really going to use them again until we understand stress states and have some failure criteria in mind, and then we'll talk about how these effects go there. Yes?
At fundamental level, what is the mechanism for strain hardening?
What is, at a fundamental level, what is the mechanism for strain hardening? The mechanism for strain hardening is the buildup of dislocations. So if you think about what we talked about last time with, there was like a crystal structure, right? Like I'm just going to draw it real quick again here, like this. All right, so we have like a crystalline structure, right? And then we start to apply some kind of shear strain, right? And we move those atoms over such that they slip to the next spot, right? And minimize their energy again. So when we do that, if you think about this lattice as not just being these two little unit cells, but being very large, then we're going to introduce sort of these stretches in the lattice, right? So we could have, I'm just going to draw it like this for lack of a better way to do it. So I'm going to draw kind of this like picture like this, where on the top we have 5 planes all vertically aligned, but on the bottom we go down to 4 or 3, right? And so this would be like I think it's a line dislocation in that material, right? So the more that these planes slip throughout, they leave these disordered parts of the lattice in there, which essentially toughens the whole lattice, right? And so that's the mechanism of strain hardening. This also is what we try to do when we make alloys is put in contaminants, right? So in steels or other things, right, we'll put in some magnesium, we'll put in some chromium, right, for different reasons. One of those reasons is to have these sort of toughening defects in the lattice already, right? So it's a tougher material starting out at room temperature. We don't have to like, induce this strain hardening. So does that make sense? Okay, cool, yeah. All right, so we're going to switch gears now, and this is in chapter 4 of the book, and it's just the basics of stress states. So if you love geometry like I do, then you're gonna like what we're talking about. And if you like equations, we got a lot of equations, and we're gonna distill them down and come out at the end of the class with a way of describing the stress state locally in a component. Okay, and we'll have to build on it in the next lecture to solve a real problem. But it's going to give you a general equation to then apply to many different types of components. Okay. I'm just going to draw our motivating problem on the next slide, and then I'll talk about a little bit how this might fit in with your with the understanding that you already have in this area. Here's our motivating problem for today. And it is a bar with a circular cross section. Okay. And it is attached to a wall. Okay, so here's a wall. It's going to have some moment applied. Okay. And so this is like a very common problem, right? We've all studied this. This is a bar with a circular cross section under pure shear from an applied torque. We're going to call it a moment because a moment can be like a torque moment or a bending moment, right? But we'll just call it a moment for now. And so the problem that we are posed with is if we have an arbitrary point inside this bar. I'll draw a cross section sort of in the middle here. All right, and I'll draw some cross hatching on there. And we'll put a coordinate system that is at the center of the bar, but it's going to be somewhat arbitrary, and we'll talk about that. So it's going to be z pointing upward. I lied. We're going to put the origin at our point, our arbitrary point inside. So our arbitrary point inside, we'll call it P. But anyway, z is going out of the bar, and then we might have y going in some direction, like off to the side, and then x going maybe along the axis of the bar. Okay, so that is a right-handed coordinate system. Okay. And so if we wanted to know the stress, so stress at P, at our arbitrary point inside, and not just the stress, but like the a maximum stress that might describe the stress state for us. What would you do from a prior course? So I want you to take a minute, and I want you to write down some keywords in your notes if you're writing, or if you're not, get some keywords in your mind of how you might start this problem from whatever classes you've taken before. Okay, so I'm going to like set a timer on my phone for like 30 seconds so everyone can have some quiet and think. All right, so you've had a moment to think about it. So now I'm going to give you another couple of minutes to talk about it with someone near you. See, we have some go-getters who already started doing that. That's good, right? So talk about it for a couple of minutes with someone next to you. And if you don't have someone next to you, you can move. But I'm not going to make you, since this is like a graduate level class. I'm not going to make you. But take the next couple of minutes and just talk with someone next to you about what approaches you know, what principles you might apply to solve this kind of problem. Oh man, natural stopping place. Okay. All right. So it's been almost 2 minutes. So tell me some keywords of approaches that you have learned or that that you've practiced in solving problems like this. Mm-hmm. So he said you chop up the piece, right? So if you want to know the arbitrary or the state of stress at that arbitrary location P, you chop it there, right? And then you have, you can draw more free body diagrams, okay? Yep, okay. More things? Okay, something with the moment of inertia. Okay. Balance of forces and moments, right? Okay, those are all very good things, right? Yep, okay, neutral axis. So we're talking about Bernoulli beam theory, right? So that's good. That's a good starting point. What if we didn't know anything about Bernoulli beam theory though, right? So we still have some ways to go. Right, if we push this problem a little bit further, right, what kind of stresses would you expect in this bar between normal stress and shear stress? Those are the kinds of stresses we have, right? Shear stress. Okay, good. Your intuition is on point. Okay. So at that location, or at any location, if this is a cylindrical bar under pure shear, then we have shear stress, right? And if we think about equations, we remember maybe something like TR over J, right? Something like that. That would be the shear stress throughout the bar, where R is the radius. And if we're at the maximum radius, shear stress is highest. And so the maximum shear stress in this cylindrical bar is at the exterior of the bar, right? At every location. Okay. So that's kind of what you may have learned about before, right? And you compare that shear stress to some other material property stress, like a yield stress or maybe even a failure criterion. And then you said, you know, whether the bar was going to yield or not, or you calculated a stress, right? So intuition is on point. Good. For those of you who have been graduate students for a while, you may have gone a little bit further in an elasticity class and defined things even in more detail than we're going to today. So you might have put sort of elastic constants in a stress tensor and done things like that. We're not going there in this class, all right? So we're going to stick with sort of a strength of materials kind of formulation, but I'm going to show you where some of those equations that you've used in the past have come from, right? Does anyone remember Moore's circle? Okay. We're not going to use Moore's circle, but we're going to look at the equations that gave rise to Moore's circle, right? Moore's circle is a way for engineers to think about where things lie on a circle so that they can imagine stress states and rotated stress cubes and things like that, right? So we're going to expand our vision a little bit from the Moore's circle today. But at the end of it, you'll recognize some of the equations that come out, okay? So let's think about definitions of stress at this arbitrary point P, okay? So some things that are going to help guide our thinking today are these. The first one is there's internal equilibrium at every point. So you learned this back in statics, right? If I cut this bar, no matter how many pieces I cut it into, every piece has to be in static equilibrium. And so that means at every location inside, we have to have internal equilibrium, right? So I'm just going to write static equilibrium below that. Okay. And so then if we use that and we zoom down into some infinitesimally small cube of material, that cube is also in equilibrium, right? So we're going to talk about that cube. And that cube is going to be our local stress state, okay? So that's how we're going to think about how we go from macro scale down to the stress state at one point, right? So a point, if we go back to sort of mathematical definitions, has no volume, has no area, right? It's really, it's kind of a 0D thing, right? So what we want the local stress, because when we are talking about components, they don't just fail at some arbitrary location where we don't know where it is beforehand. Like, oh no, let's just use a rotating shaft until it fails and then figure out where that was. No, it's going to fail at a specific location, right? And so if we can define that location by the local stress, then we can pinpoint where that thing is going to fail. Okay. So first we'll talk about, we'll define the variables on this stress cube, right? And you may have seen this before, but just follow along, get a refresher. So we'll draw some axes here. Whoa, that is like the waviest axis. Okay. All right. I want to try something real quick. Hang on. Let's see if I can rest my hand and provide a barrier and it won't. I can rest it down a little easier. Nope. Okay. Never mind. Ooh, that's a lot better. Okay. So I'm going to draw a set of axes here. We're going to have X, Y, and Z, another right-handed set of axes. Okay. And then I'm going to draw a cube on these axes, drawn in a different color. Okay. It's good to practice drawing and sketching 3 dimensions. And so we will have some dimensions of this cube related to the axes. So we're going to have one on the top, dy, because it goes along the y direction. So that's our dimension there. And then we'll have correspondingly dz, and dx. And because this is a cube, these are all equivalent. And then on the faces, we will have normal stresses. Okay, so I'm going to draw those. I think we'll do normal stresses in red. So we'll have a stress, we'll call it sigma, and it's going in the y direction. We're only going to use single subscripts in this class, so that's going to be sigma y. And correspondingly, we'll have stresses in the other direction, sigma z and sigma x. And then this cube is in static equilibrium. So I'm just going to draw the ones that are facing us because those are the ones we see coming outward. But there are equal and opposite ones on the other faces. So for example, okay, I'll draw one of them. Like if we have another sigma z coming out of the bottom there, right? And so this is the convention for stresses. And if they're going outward, it's in tension. And if they're going inward, or if they're negative, right, that's what we define as compression. Okay, so that's pretty straightforward. The shear stresses are easy to get mixed up, so we'll have a specific convention to describe those. And so we're going to call shear stress tau. So we'll have tau ij. And we'll have 2 subscripts for all the shear stresses. The first one is the direction of the plane, or the normal to that plane, on which it acts. Okay? So the normal, sorry, I'm going to write this clearly. Direction of the plane on which it acts. Okay, so the direction of the plane on which it acts. And we always describe the orientation of a plane by its surface normal. So I'm going to write normal underneath it. Okay, and the second subscript is going to be the direction of action. So that one's easy. Okay, it's just the first one that trips people up. So if I were to draw a shear stress on the top of this cube, the top of the cube, its normal goes in the z direction, okay? And so it's going to start, if I draw a shear like that across the top, it's going to be tau, and it's going to start z, because it goes on the z face, right, defined by that normal. And in this case, I've drawn it in the y direction. So it's tau z y. Yeah. If we want to draw the other component on the top of this cube, right, we can draw it like this. And it's going to also be on the z face, but now it's going in the x direction. So it's tau zx. Come on, pen. Okay. Tau zx. All right. And so we can draw those same shear stresses on the other faces. We don't have a tau zz, right? Because we can't have, if we're on the z face, we can't also act in the z direction. That would be coming out. That's a normal stress. So these are the conventions that we have. If we draw the other ones on here, I'll draw them on the front face. We'll have 6 all together, right? So if we draw one upward here, we have tau y z. If we draw one coming forward on that face, we have tau y x. And then on the front face, tau x z and tau x y. Okay, so I know it's getting very messy, but if you follow the conventions of the plane and then the direction it goes, then you'll always get it right. Then we have to define what is positive. So if you look at these shear stresses that I've drawn on here, the arrows are pointing toward each other. For example, tau xz and tau zx. They point toward the same corner. And so this is the convention that they always have to point toward the same corner. And that's for static equilibrium purposes. And positive is the way that I've drawn it here. And positive means that they're in the direction of an axis whose sign is the same as the sign of the axis of the outward normal. So that's a lot of words. And I'll just circle some things here to show you what it means. Okay? So let's say we have tau zy. It's the very first one that I drew up here on the top. I'm just going to circle it in yellow. So tau zy goes that way, right? Well, if I've drawn it and it goes in the same direction as a normal from this y-axis, then it's positive. Okay? And so that's the definition for positive shear stress. Okay? If we have a stress state where the shear stress acts the other way, we can either draw it the other way or just call it negative. I think for the most part, we're just going to use signs to show the direction here this semester. All right, so if we draw all of those on there, then we have, not including the ones on the back, right, because those are equal and opposite, we have 6 unique stresses to define the stress state. So we have sigma x, sigma y, sigma z, and then we have shear stresses 2 on each face, right? So we have 6 plus 3, that's 9 components. That is kind of a lot to have to define for this stress state, especially when we know it's a very simple one. So we're going to simplify it a little bit. The first way that we're going to simplify it is using symmetry of shear stresses. So I'm going to go to the next slide. I'm going to draw only one face of this cube now on the zy axis. So take away the cube extension out of the plane in x, and we'll just focus on z and y. So that's z, that's y. And so if we draw our cube on here, come on, cube, okay. Or now it's a square, not a cube. Right, then we'll have sigma z going upward, and then equal and opposite, and sigma y on the left and right. And now on the top, we've kind of collapsed this down into 2D. Okay, so I had green for shear stresses. So we can draw a shear stress across the top of the cube facing to that direction. And that is on the z face in the y direction. So it's tau zy. And then we can also draw the one on the right face, right, which is tau yz. And we draw the equal and opposite ones like that. Okay, so now everything's in static equilibrium. Well, if we look at the origin right here of our system, and we just do a simple thing that we know how to do from taking statics, which is sum of moments around the origin, okay? We can do that with the shear stresses, okay? We're going to ignore the normal stresses for now, but if we just do the shear stresses, then we can write down an expression like this. Let me go back to a dark color. All right, so the sum of moments, and that's going to be around the x-axis, and we will take counterclockwise positive. So we will say that tau yz, right? So that's a shear stress. It's not a force. And so if we need a moment to be a force times a distance, we need to convert this into a force. This is acting on the y face of our cube, which has the dimensions dx dz. So I'm going to write that here. And this is just trying to get a force from the shear stress, because when we sum moments, we need a force times a distance. And the distance acts dy away from the origin. So that's our first moment from tau yz, is tau yz times the area over which it acts times the moment arm of dy. And then we also have tau zy across the top, and so that is acting in the opposite sense with respect to our moment. So we're going to do minus tau zy. The area over which that one acts is, let me think about this again, xy, right? So dx dy. And the moment arm now is dz. Okay. And that subtraction is going to equal 0. If we're summing the moments, we know that the thing is in equilibrium. So you can see now that each term shares dx, dy, dz. Those cancel out. And then these two terms are equal to each other. So tau yz is equal to tau zy in magnitude. Right? And so we can use the symmetry of these shear stresses now to reduce our 9 components to 6 components, if this, in fact, is a cube made of square surfaces. So we have sigma x, sigma y, sigma z, tau xy, tau xz, tau yz. Right. Okay. So those are our 6 components. So that's helpful. Okay. And that's what's going to move us forward. So if you think back now to our motivating problem, and now we have these 6 stresses, we could actually assign one of them to our shear stress from torque, right? We could say, depending on the axes, we know it's going to be in this kind of plane, right? And then we could assign some magnitude to it based on beam theory. And then we could describe the stress state like that, because we know there's no sigma x, sigma y, sigma z, right? We don't have any normal stresses. All we have is the shear stress. Okay. So we could do that, and then we could put it through our Moore's circle filter if we want and say, sure, it's in pure shear, but we can also rotate that stress square to represent the stress state in terms of only normal stresses, right? We can do either one, okay? And so the stress state here is definable in multiple ways, okay? Let me just do a time check here. So I'm going to draw up some geometry as we go into the second part of today's class. And what we're going to do is we're going to take the cube that we drew before, and we're going to cut it at an angle. And we're going to use that angle to describe the stress state. Okay? So what we're going to do is we're going to cut the cube. Okay? Sort of in an arbitrary plane, and then we're going to define the geometry of that. Okay, so here we go up. We still have our z, x, y. And we can go and draw some points here, right? So I've drawn the axes and put some points on there. But instead of drawing a cube, I'm going to draw a plane like that, okay? So now instead of a cube, I've got this triangular prism where 3 of the faces align with the faces of the coordinate system, okay? So we still have our faces, right? But now they have slightly different geometry. Okay, so let's define some things that are happening on this cube. So we can still define the stress state, right? And some stresses that are coming out of the normal direction. So we still have sigma x, sigma y, sigma z, right? Coming out like that. And we still have the shear stresses defined on those faces as well. Okay, I'm not going to draw them all here because it gets very, very crowded. And then what we're going to do is draw a surface normal. Okay, let me draw that in a different color. So we're going to start at the origin, and we're going to draw a surface normal. Okay, and the normal defines the plane that I've drawn there, right? And so that surface normal is going to be defined by 3 angles from the different axes. Okay, so I'm just going to try to draw those on here as the most clear way I can. So that normal is related to the y-axis through some angle beta. It's going to be related to the x-axis through some angle alpha, and it's going to be related to the z-axis through some angle, whoops, that should go all the way around, through some angle gamma. Okay, so we have alpha, beta, and gamma, and those will help to define that surface normal. Before I move into more geometry and defining the general stress state, I think we're going to stop lecture 2 here and take like a 10-minute break, and then we'll do the second lecture for today. Okay, so I'm going to stop here.